Hi, everyone. Welcome to the Machines live stream. This is for simple machines in Division B and compound machines in Division C. And my name is Cruz Soto. I worked on this presentation with another fantastic high school graduate. Him and I wanted to bring this to you together, but unfortunately he was busy today. So no worries, we'll be able to handle this on our own and wish him the best of luck in his endeavors. And wish the best of luck to you, competitors, because we're hopefully here to help you in doing whatever it is you need to accomplish for this now virtualized form of the machines competition. And we're getting live updates every day about what the Science Olympiad organization is planning nationwide. And so I hope that this can bring some clarity as to what the test component, as well as a little bit of the build component, or the hopefully build component, will bring. So yeah, let's go ahead and get started. So to talk about the machines events, we need to first talk about what simple machines are. And this, of course, is going to be about as far as most of you Division B students go. But for the most part, I see a lot of high schoolers as well who can't get started on compound machines without knowing what a simple machine is first. So as it says there, it changes the direction or magnitude of a force, because it can do both. We'll see examples today of things that can change both direction and the magnitude. And keep in mind that a simple machine can only has to do one of those things. So for example, we have over here on the right, this is an example of a gear, coaxial gears or a wheel and axle, which can change both the direction and the magnitude of a gear or of a system. Something like a belt could be changed, a rope can have the direction changed. And then of course a standard pulley or even a wedge can change something like the magnitude and direction of the force. So the first thing that you're going to face on the test is this idea of what free body diagrams are. And ultimately, even if you have a very simple physics problem, it is always best to start, especially when you have difficulty processing a question, with what a free body diagram would look like. This was supposed to actually be two different pictures so we could draw out the free body diagrams. But I guess the slides aren't working as well as we'd like today. So yeah. So you can see that we have a different components of the force that are acting on the block on this ramp. And one of the first things that we can decipher from looking at these forces is you can see that mass and gravity are going to be going straight down to determine gravitational force. That's the first component that you always have with any sort of device, as long as it doesn't state in the problem that your item is massless or is grounded. So for example, you could see that you have a stationary ramp there. You would not want to draw the free body diagram for the ramp, because the ramp is not an active component in the system. It's merely providing the change in angle for that block, but it is not acting upon it in any way other than the normal force. And as you can see there, the normal force is a force that acts perpendicular to the direction of the surface at which a block or item is conjoined. So if the block were just flat on the ground, the normal force of the earth is pushing up against it. And so this block and this ramp are known as what are called an action-interaction pair. And so these pairs are basically objects other than the earth, that an action-reaction pair is an item interacting with another item. And what those things do is they act on principle of Newton's third law, which is the idea that any two objects will exert an equal and opposite force on each other. And in this case, you have the example of the normal force. And so the normal force of the ramp on the block is equal and opposite to the force component of the block on the ramp. And in that example, it would be this block here, the magnitude of the gravitational force multiplied by the cosine of the angle there. And that would be the component to split that up into what we would see as J and I components there, which give the cardinality. And it's a common way of saying X and Y in a more complicated and physicsy way. And now that force of F is just an example of why we would see a force pulling on that block. Now, so the force F can represent two things. So first, a capital F like that one is talking about a force, a pulling force. Now, usually you'd see something like a string or a rope attached to that block, or sometimes you'll see that without any sort of rope. And when you see nothing pulling on that block, you'll often see that miniature F. Usually you won't have it combined with a capital F. I'm not sure why the capital F is there. That's not usually the nomenclature you see on an exam. but instead you'd see that miniature f, which means friction, force of friction. Yeah. So just making sure that we know all the components that we have there. So let's talk about another thing, which is torque. So torque is, like it says there, not just, yeah, there it is. It just says spinny force, which is true. It's force applied at a distance from a fulcrum. So a fulcrum is a point at which an object can spin. So an example of a fulcrum would be something like a lever. A lever would have a fulcrum at one end, and you'd apply the force at one of the other ends. Somewhere along that line, and you can determine the intensity of the torque based on the direction at which that force is applied. And so I actually talked about that, completely skipping over the second thing that I wanted to talk about, which is Newton's second law. Force equals mass times acceleration, or in its more common form, mass times the derivative of velocity. Now, not all students in high school are required to take calculus. However, I find that it makes problems a lot easier because a lot of the time you might be given velocity and have to generate a graph to yield acceleration, and that would take some time. So to save you time, if you have taken calculus, I highly recommend that you memorize this definition because it's actually the more formal one. So now we're giving just examples of simple machines. So you have these 6 simple machines as will be used in the competition for simple machines. And in compound machines, we'll actually see a 7th simple machine, which is the gear. Gears will be used in compound machines for Division C. If you're Division B, do not worry about gears, but we're definitely worried about the other 6 of these. Yeah, so we'll be talking about some of these with a bit more examples in the following slides. All right, so when you have simple machines, you have 2 different concepts known as ideal and actual mechanical advantage. And as the names imply, ideal is going to be something that is ideal. It's a theoretical concept. It is dealing with something that would exist in a world where you have no forces that are going to detract from the system. We have a lossless system. So that would basically mean a world in which you have no drag force, you have no frictional force, and you have no other force that's going to take energy away from the system without giving it back somehow. So for example, the acceleration due to gravity is keeping more or less energy within the system because it's actually giving something what we call potential energy. And so even though you can decrease potential energy by being pulled down by gravity, that potential energy being converted into something like kinetic energy is therefore taking away, not taking away energy from the system. It's just converting it to a different form, as opposed to something like drag force would minimize the effects of the motion of the system, which is taking away energy. So ideal mechanical advantage deals with a world in which this doesn't exist. So you would have something like a lever, which now actually, let's see, is that our next slide. Let's talk about our lever. You see as a lever, we're going to have our force of effort at a certain distance and our force of load at a certain distance. And now that fulcrum might be a little rusty. You know, you might have some corroded iron in there that's going to slow down the effectiveness of that fulcrum there. But the ideal mechanical advantage would simply be the distance that the effort is applied to divided by the load that the effort is applied to. So that would probably be something like, it looks like the load is halfway at that point. So it looks like your mechanical advantage would actually be 2. You would have a mechanical advantage of 2 when you have that second class lever there in the center. Sorry, I failed to simplify. And so that's dealing with ideal mechanical advantage. And actually, we just have another presenter who hopped in. Sarah, could you unmute yourself and possibly introduce yourself and talk about actual mechanical advantage for us? Hello? Have I been silent the entire time? That would be pretty unfortunate. The meeting host will let you in soon. Oh, she's facing complications right now. Let's take care of that real quick. Oh, wait, am I the host? Oh, wait, I'm the host now. Never mind. That's right. I need to let her in. Hold on a second, folks. We're having some complications. Let me go into my waiting room. Can I access the waiting room? It still says I'm not the host. Admit. There we are. Awesome. All right, Sarah, are you in?
Yeah, I'm here. Thanks.
Okay, awesome, Sarah. So we were just talking about actual mechanical advantage. So if you could go ahead and just introduce yourself, and then I'll put on the mechanical. Can you see my screen?
Yeah, I can. So,
Okay,
hi, I'm Sarah Wheeler. I'm a member of the John Adams Science Olympiad team from Indiana. I'm a senior this year, and I'm also an IB diploma candidate.
great. All right, so we're talking about the ideas of ideal versus actual mechanical advantage. I just discussed a little bit of the difference between the two, and as well as what ideal mechanical advantage is. So if you could go ahead and elaborate on that and introduce us to actual mechanical advantage.
So, as opposed to ideal mechanical advantage, actual mechanical advantage factors in real world conditions such as friction, structural integrity, and air resistance as a relation of the output force to input force. So, of course, it is more accurate in the real world.
Great. Yeah. So that's right on the money. So we're analyzing the force output and force input. So even though the distance, friction, and structural integrity have no bearing on something like the distance, I could be 1,000 miles away from you, and that would not change the integrity of my car or the integrity of a rope that I have between you and I if we're standing a couple feet apart. However, analyzing the force input and output would definitely demonstrate that. So let's talk about some specific cases of mechanical advantage in simple machines. So Sarah, if you can go ahead and talk about the difference between first, second, and third class levers for us.
So obviously, as you can see, there are three different classes of levers, and what makes them different is the first class lever has both an ideal and an actual mechanical advantage of one, and usually only changes direction of effort force, whereas the second class lever has an ideal or actual mechanical advantage that's always greater than one, and it changes direction and magnitude of the effort force. And then the third class lever is pretty much the opposite of that. So it has an IMA or AMA of less than one, but it also changes the direction and magnitude of effort force. So a
Cool.
lever in general is simply a plank or a rigid beam that is free to rotate on a pivot or a fulcrum, as it's also called.
Sarah, if I can ask you a quick question, did you do this event in high school, or are you doing this event this year?
Both. I competed in machines at a few different invitationals last year. I studied for it, and I helped build the machine itself.
Cool. So what I'm going to do actually is I'm going to kind of change the order of this presentation. Hopefully our viewers aren't too upset by my meddling in the order. But could you give us like a quick rundown of how the concepts behind levers or anything you really want to say about the build portion of the event? Kind of just a disambiguation. Like it could be casual. It's not me. Obviously, this is a little informal. So since we kind of replaced, Sarah came in to replace my partner who was supposed to present with me today. And so she might be a little frazzled. So I'm sorry about that.
A little bit.
Kind of throwing this at you.
It's all right. So pretty much the idea is that you build a machine that can actually measure the ratios between the weight ratios between two different objects as accurately as possible using levers. So if I remember correctly, ours used a second class lever and a third class lever like connected at one end, and you would move the weights around on the machine to sort of determine what the ratios were. So yeah.
Do you have any like build tips for that? Oh, sorry, no, that's fine. Yeah. Hello.
Sorry, I thought you were going to continue on.
Hello?
Sorry, I thought you were going to say something.
Oh, no, sorry. I was just having issues with my headphones is all. Sorry about that.
Ah, okay. So for the actual testing itself, generally the idea is that so they'll give you masses labeled A, B, and C. They're generally made so that it's not obvious by just looking at them which should be heavier. I mean, obviously you can tell by picking them up, but sometimes it's quite subtle. So what happens is the um like the event supervisors will come around and they will monitor you um as you weigh the three different objects that you pretty much attach to your machine, and then you're given a set amount of time. I don't remember specifically what it is, but it's reasonable. It can be done. And
If I
so
remember
you
correctly, it's like about 4 minutes.
yeah, okay, makes sense.
Yeah, here we are, not to exceed 4 minutes. And they do it as a factor of, if I'm not mistaken, because I helped coach this event a bit, but I never actually, and I've done tests on it. I've written tests for it, but I've never actually competed in it. So if I remember correctly, the faster you do it, the more points you get.
Yeah, it is sort of like a value proposition though, because it is a factor of both how quickly you do it and how accurate you are. So it's important to sort of weigh if you want to go to the very last second but be very accurate, or if you want to be slightly less accurate but faster.
So do you have any strategy or build tips for the viewers today?
Well, one thing that's important to consider is partly the structural integrity of your machine itself, because that's not always something you think of, because obviously you want it to be accurate and you want it to be precise, but it's also important to make sure that it can handle the heaviest of the weights that they'll give you, which I believe they've done up to 1,000 grams. So you want to make sure it doesn't tip over or anything like that, because that can not only ruin your test, it can also cost you a lot of time if you end up having to modify your machine. So then instead of studying for the test or actually like really getting very precise of calibrating the machine, you have to waste your time rebuilding it.
Great. So now we're going to get back to a bit of the test portion and talk more about, oh, hopefully I didn't ruin anything there. Give an example of some of the questions that we're going to have on the test. And I thought the best way to do this would be to actually take one of the problems I got in class. This is pulled from MITx, which is one of the servers that we at MIT use to teach classes online in these troubling times. And I've modified this problem and removed friction, but we're going to assume that there's friction there when talking about these problems, and try to find a solution of a static system. And we need to make sure to capitalize on the difference between a static and a non-static system, because machines and compound machines and simple machines will only deal with static examples. And we're going to talk about what that means. So I'm going to go ahead and I think I already took a screenshot of that. We're going to move it over into here, which is a worked example that I have. Hopefully it's pulled up. Oh, that's weird. This one I got a picture of it. Guess not. There we are. And I'm going to jump in here and we're going to do a quick worked example of what something like this would look like if you're at home, or if this is a recording, or if you don't have the effort to do this now and then you want to follow along later, we can go ahead and do any of those options. One of those first things that I'm going to talk about is we're going to assume that there is a force. We're going to call it lowercase mu here. And it's like going to be static. And so we're going to talk about a few things about this system before we solve it. So first of all, let's identify all of our active components. So we see here that we have a pulley that we're going to assume in all of these scenarios is massless. Both of these pulleys carry next to no mass. All right. So this pulley here is purely acting to change direction, as well as this pulley here merely again acting to change the direction of the force. So what we're seeing here is a system that looks dynamic but is actually a static system. And when you're given that something is a static system, that basically means that for any given object, let's say mass 1, any object is going to have a sum of the force components. So that's indicated by a sigma m, a sigma f. And so that is going to be equal to any of the forces acting on that body. So again, let's follow some of the steps that I laid out earlier in the presentation. So the first of which is going to be drawing free body diagrams for everything. Now, for the sake of this presentation, because this pulley carries no mass, that means that it's not changing anything other than the direction of the system, and it can't change the magnitude of the force. So because of that, we're going to assume that we're not going to draw this pulley's free body diagram. Now, you see that this pulley here, however, has a mass attached to it, mass 2, and we're going to deliberate this system right here. We're going to treat this as an object, and then we're also going to talk about mass 1 here as well. So let's first off draw the free body diagram of mass 1. So mass 1 is on a ramp right now. So we're going to draw a nice rectangle. There we are, or that's a square. I want a rectangle. Thank you, sir. And now we're going to have mass 1 here. And now we have this on a ramp. So we have the force here from this rope being applied to it. So whenever you have a rope, that force is going to be called force tension. And we usually denote that by having a capital T. For any of you guys in physics C, mechanics, or physics C, electricity, magnetism, having already taken mechanics, you should already know more or less a lot of this content. So we have the force of tension there. We also, as we discussed earlier, we have mass gravity here. And then we have a normal force that is pushing up here. Keep in mind that the length of my arrows is not at all representing the magnitude of these forces, merely the direction. And now we have something interesting here, which is a coefficient of friction, or friction. And now what friction is friction is going to oppose the direction of force on anything. Now, if you notice, if you have a frictional force, for example, I have here my bed, this mattress has a lot of particles on it and it's very rough. So if I push my hand against it, I'm going to have the force I'm applying to it in this direction opposed. And if I pull back, I'm also going to have it opposed. It's going to tug me back a bit. And so what you realize is that when you have a force of friction, is always going to oppose the direction of your force. And so the good thing about this example is that you're given a static system. So when you have a static system, you can kind of leave it up to interpretation which direction the force is going to go, depending on which of these forces is pulling on the strongest. So what we see here is that you have a force of tension here. And so since this is the predominant force in our system other than gravity, we're going to assume that the force of friction is pulling in this direction. The reason we have that is because this is our predominant force. The force of tension is acting above all other forces here. We don't have anyone pulling this block down. We don't have a rope here. We don't have anything except for gravity. And gravity is typically a weak force when compared to the force that's applied by a human being or by an external rope. So we're going to assume that the friction is acting in the opposite direction of the predominant force in our system, which in this case is tension. So now we have force of friction, or also you can show that as mu s. So mu s is called the coefficient of friction. And you can have two types. You can have coefficient of friction s such that you have a static system, and you have coefficient of friction k such that you have kinetic friction. And you in this event are never going to deal with kinetic friction, simply because kinetic friction implies that you are moving. So we know for a fact that any system you're going to get in this event is going to be a static system, and it's not going to deal with dynamics. So coefficient of friction when you're static basically means the friction that you need to overcome to start moving. And since none of our objects are ever going to be moving, we're assuming that this frictional force is not being overcome. So we have the free body diagram for this block, and now we're going to move a lot faster through this problem because of it. So next we have mass 2 on this pulley. We have here our pulley. Oh, that's not a pulley. I don't know what that is. I don't know what that is either. Come on, please. Yes, fantastic. All right, now we have mass 2 pulling down here. And since mass 2 is the only mass in this system, because again, we're assuming that this rope here has no mass, and we're assuming that this mass here of the pulley also contributes no mass, we're going to go ahead and assume that the whole mass of this object here is that of mass 2. And so, I don't know, sorry about that. If you can scroll up here, we have a rope coming up here that attaches to a rooftop here. And then we have this rope here, which attaches to the other pulley and then goes this way to actually become this rope here. And then you have your other pulley there. So we know for a fact that this force is the force of tension, the same one from over here. These are the same force. And we also know over here that because this is all the same rope is never going to change tension. The tension and the forces, at least within the confines of this event, you're never going to have the same rope express a different tension unless there's a binding point. So for example, maybe you have this rope is tied up here, and then you have like another part that's hung down. So this section is separate from the rest of the rope. These are separate because there is a binding point here. It's tied here. So because of the fact that you don't have any binding points for this rope up until you reach this roof here, we're going to assume that the tension in this rope is going to be the same everywhere, which basically means that there's also a force of tension here, which is great. All right. Well, what that means is that keep in mind that since our system is static, that means that this pulley is not moving. So whatever force wherever mass 2 gravity is here, we know that if we were to add the forces for this block here, the sum of the forces is equal to 0 because we're not moving, times mass 2 times gravity, or actually since we're going downwards, this block would be going downwards. We're making this negative, plus 2t, which is the upward force of tension applied in two places, here and here, plus 2t. And now we have an equation that basically says 2t is equal to mass 2 gravity. We have an equation here. That's great. This is going to be a very important equation later in the problem. Now, secondly, let's look at this first system. Let's add the forces of this first system here. So we know that we have the normal forces acting perpendicular to the surface. So the normal force would actually not contribute directly to this problem. It'll actually contribute in a more indirect way later. You'll see that. So we have the force of tension and a component of gravity, because gravity is kind of acting at an angle. So there's a part of it that's acting directly down, which is actually equal to the normal force. But you also have a direction here where this is getting pulled. So the block is getting pulled down a little bit by gravity, though not as much as it is being pulled by tension here, which means that the force of friction is still going to act opposing the direction of movement in that one, in the direction of the tension. So let's break it down. So we have mass 1 times gravity multiplied by, we have an angle theta here that this slope makes with the ground. And now we have sine theta. And why is it sine theta? Well, if you look at how this is broken down, we actually can figure out that if this were flat, if this were a flat slope here, the component of gravity would actually be 0 because gravity would be going straight into the ground. And we know that when we have two curves, we have sine and cosine. If you were to graph these two, sine is equal to 0. Sine of theta is equal to 0 when theta, or the angle here, is equal to 0. So if this slope were flat, then there would be no gravitational force pulling you down this ramp. However, because of the fact that there is, theta is greater than 0, we don't know what the value is, and as such it's acting. However, if this were cosine, that would mean that when this slope is 0, when theta is equal to 0, cosine would be 1. This is 1 right here. So if cosine of 0 were to be 1 in this situation, and we applied it when it were flat, that means that gravity would have to be this way. Gravity would have to be perpendicular to the ground. And that doesn't make sense. That doesn't make sense in this situation because, as we know, we're not flowing sideways. I'm not floating into my wall due to the force of gravity. So that can't be correct. So that means that we have to have sine of theta. And you can also break this down by proving mathematically that this is equal to sine theta. This is equal to theta here. And we know that we want this component here that I'll highlight it in yellow, because yellow is a pretty color. We want this component here, and we know that sine is equal to opposite over adjacent. So if we took the magnitude of this force, which is mass 1 times gravity, and we multiplied it by sine theta, we would be left with the opposite, and we'd be left with this component of the force. So we're going to go ahead and multiply it by sine theta. And this is acting downwards. This is pulling us down the slope, so we're going to make it negative. And then we're going to add tension. And then finally, we have one other force here, which is the effect of friction. And friction is always going to be acting in the opposite direction of the force of whatever we say is positive. And since we say tension is positive, because tension is the predominant force, we're going to say that friction is acting downwards in this direction. And friction, force of friction, which I would denote like this. Some people from earlier in the presentation might have seen it like this, which is ugly and disgusting, and I hate it. If anyone uses that on an exam, I do not hate you. I'm sure you're a very lovely person. That's just not how I would do it. Any of my future professors, please do not penalize me for having said that. I'm sure I'll love you all too. But this is how I'll write it. So the force of friction is equal to our coefficient of friction, which is an unknown number that changes for surfaces. So obviously something like ice is going to have a very low coefficient of friction because it's very slippery, as opposed to something like sandpaper is going to have a very high coefficient of friction because the force that's generated by it is going to be a lot because it's very hard to slide your hand across sandpaper. So that's going to be a very high or low number depending what our slope is made of. And in most classes, this is going to be wood, which generally has something, I think it's around like 0.2 or 3. I don't know. Don't quote me on that. That's just, I'm trying to remember something that I took 3 years ago. So you have your coefficient of friction, which is denoted by this symbol mu times s, which in class will probably look more like this, which looks like a weird U. But to each their own, multiplied by, and look, here it is, our normal force, or the force that's acting directly into this plane, directly perpendicular to our force of tension. And so how do we calculate that? Well, this is where our cosine comes in, because cosine would make this theta turn our mass gravity component into this vertical component. It's perpendicular to here. And we know that cosine of theta is equal to our adjacent over the hypotenuse. So if we take this adjacent component, we can know that the adjacent component here is going to be equivalent to mass 1 times gravity multiplied by cosine of theta. Because we know for a fact that whatever this is, I'll call it x vector over mass 1 gravity, that this line here is going to be equal to cosine of theta. So if we just redistributed this, we know x vector is equal to mass 1 gravity times cosine theta, which is fantastic, and that's what we want. All right, hopefully that made sense. If it does not, hit me up. So our force of friction is now going to be equal to coefficient of static friction times mass 1 times gravity times cosine theta. And it's going to be negative since it's going the opposite direction as our tension. So now we have this cosine theta minus that. And now I can safely say that we are more or less done with this problem. All we need to do is combine stuff. And it depends on what you want to get. You can get pretty much any value in this problem. You could solve for G. I mean, not that you would need to. You could solve for mass 1. You could solve for your coefficient of friction if you wanted to. You could solve for pretty much anything in this situation. Let's say right now that we want to solve for the value of mass 2, right? So let's say we wanted to solve for that. So the first thing that we do is say that tension is equal to mass 2 gravity divided by 2. Great. Now we're going to take that and plug that into this equation that we just got here. And we know that this is also equal to 0, by the way. So now what we're going to do is plug that in. So we have negative mu s g, so mg, m1g, sorry about that. This is m1g cosine theta minus m1g sine theta plus Now that's m2g over 2 is equal to 0. And this is equal to 0. So if we want to solve for mass 2, then all we need to do is move everything that doesn't have mass 2, in this case, all this stuff, to that side. And now what we're going to do is just add. So we're going to add mu s m1g cosine theta, and then we're going to add m1g sine theta, and that'll move them over to the other side of our equation, which will give us m2g over 2 is equal to mu s m1g cosine theta plus m1g sine theta. And then we get to divide everything by the gravity, because don't we all love to get rid of gravity? Because we have gravity on every single one of our, as a coefficient on every single one of our numbers. I'll call them numbers for now, even though they're technically force components. And now we can simplify this by multiplying everything by 2. And we multiply this whole thing by 2. And finally, we get mass of 2 is equal to 2 mu s m1 cosine theta plus mass 1 sine theta. Let me get a couple quotes there. And now we have the value for mass 2. And you could solve again for pretty much anything. You could solve for theta. You could solve for mu of kinetic coefficient of friction for static friction. You could solve for mass 1. But in this case, we solve for mass 2. So this is a really good way of just setting up your problem and always remembering what they want you to solve for. So this is just probably a really long, I think that took us about 18 minutes to solve. But that's just because I talk way too slow and I explain way too much and understand too little. So I hope that that helped a bit. And this isn't what I solved for in class. In class, they asked us for something different. So the answer that we have listed here in the presentation is not the same as the answer that I was asked for. And then also in class, this was a dynamic, not a static system. So we have, as you can see at the bottom there, we have mu k, which is a force of kinetic friction. And you solve that completely differently. So please do not try to learn dynamics for this event, because it's not going to be very useful to you. It'll be awesome to show off to your friends, but not very useful. So we're going to talk about some more compound machine examples really quick. I'm sure many of you already know what those are, so we didn't want to spend too much time on them. But I don't really need to break it down. Standard examples are talking about two wedges combined together as if they were levers being pulled together by human force here on scissors. And then in this case, very interesting, you have the wedge on a stick, the axe. And something interesting about that is that a fulcrum doesn't necessarily have to be a solid pivot point. It actually is where your hand lines up with the axe. So you are actually acting as the fulcrum. So you would have your arm or your hand wrapped around that axe and you'd be swinging it. And the fulcrum in that case would actually be, you'd actually have two fulcrums, the first of which would be your hand, the ball point of your hand. And the second would be your shoulder or your arm right here, because you'd be swinging in this direction. So that's pretty interesting. And we talked about the bill portion already. I'm not sure if we have anything else. Oh, I think that was more or less it. I hope that we don't have actually, I hope we do have a lot of questions, because this was a kind of a very long ride through compound machines and simple machines. And I hope that this is helpful to you all in your events. So if we don't have any questions,